The goal of this video is to show you how to work with multiple linear regression in R. So we're going to work with the gfclocks.csv dataset, and you have this on your Canvas page. What you should do is just download this and place it in a folder where you can find it. I have opened RStudio here, and the next thing I want to do is just to set the working directory. Remember that to set the working directory, all you need to do is to go to Session, set working directory, and then choose directory and navigate to the folder where you have the files located. There's also other ways to do that. You can use code like the setwd command, and then under quotes you can place the path of your directory if you know it. Another way could be to just go to Files here and then navigate to the folder. For example, I'm just gonna go to my Google Drive, my drive, and I say 291, and there's the location of my file. And then if I want to go and set the working directory to this location, I can go to More, and then either copy the folder path and place it in the setwd command, or you can just go ahead and set as working directory. So all of those ways are available for you to set the working directory. If you set the working directory correctly, then all you need to do is use code to read the file. So let's read the gfclocks file. We're going to use the read.csv function. So I'm going to use gfclocks, name it, name the file gfclocks, and I'm going to use the read, lowercase, read.csv function. And under quotes, I can just place the name of the file. You can use autocomplete, and the way to work with that is just use the tab key, and if you are on the correct directory, it will autocomplete the file, so you don't need to write it completely. The read.csv function is a version of the read.table function, with the only exception that you don't have to use this separator, because it assumes that it is separated by a comma separated value. Now, it's a good practice to also use the strings as factors equal to true whenever you're reading a dataset, so that if the dataset contains a categorical variable, then it is read as a factor and not as a character. So I'm going to run that, and basically I can see in the global environment that I have 32 observations and 3 variables. You can see the variables there. We're going to use age as x1, number of bidders as x2, and price as our response. So we're going to use multiple linear regression to get the estimates of the parameters. Remember, the model we're trying to estimate is the expected value of the price. And we want to get an estimate of beta 0, which is the y-intercept, and an estimate of beta 1, which is the slope for the variable age, and also an estimate of beta 2, which is the slope for number of bidders. Now, this is a population model, and these are parameters that we don't know what they are, and we'll probably never know the true value of those. The only thing we can do is basically get estimates based on these 32 observations. So I'm gonna first name my regression 1. I can name it whatever I want, but just make sure to just know that everything in the regression is gonna be saved to this object. So I'm gonna use the lm function, use the y variable price, tilde, and then the age, that's my first variable, separated by a plus when I am putting a new variable, number of bits or biters. And then I'm going to use the data is equal to GF clocks. It is a good practice to do this way, as opposed to just putting GF clocks $H. And why is that? Because you're already telling R that your data set is GF clocks, you don't have to use the object. You don't have to obtain the object term GF clocks, so that whenever you're doing the predict function or whenever you're predicting, that solves a lot of errors. So this is probably the best way to do this. So I'm going to run that, and you can see that nothing in the output, there's nothing there, but you have a new object in the global environment. That object contains a lot of things, including estimates, coefficients, residuals. It has attributes that contain ways to predict with these models. So there's a lot of things going on the background when you save when you save the output to that object. To get the summary, you just use the summary function as you have done in previous simple linear regression examples. And in there, you can see the parameter estimates. You can see the estimate of the y-intercept, estimate of the slope for h, estimate of the number of bitters. You can see RMSE with the degrees of freedom, error degrees of freedom. And we are going to use the adjusted R-squared as a measure of the fraction of the explained variation. So now the best way to know how much we can explain on the variation, we can use the adjusted version of R-squared because it adjusts depending on the number of variables. The ANOVA, the analysis of variance, can be used to retrieve the values for SSE, SSR. So as an example, I'm just going to run that and show you that this is the value for SSE, the sum of squared errors. We want to minimize this value. And we have MSE, which is dividing SSE by its degrees of freedom. And then we have SSR, the explained variation by variable. It is a little bit different. If you want to explain it, it would be explained this way. This is the SSR contributed by age. But this is the SSR contributed by number of bitters given that age is already in. So it's an additional SSR. If you sum the two, it comes up to the total explained variation, the SSR value. But it is important to know that this ANOVA function just does it this way so that you can see the additional contribution by variable. So this is a quick example of how to use R to just get the parameter estimates. Other than this, it's important to know that we want the variables to be as independent of each other as possible, the predictor variables. So prior to doing a regression, it is important to best analyze the variables and make sure there's not multicollinearity. And you can do this by using a scatter plot matrix. And in the scatter plot matrix, you basically want to check the relationship between the predictors and the response. So as an example, I'm just going to run this really quick and show you the scatter plot matrix here. And you can see that price is positively related to number of bits. Price is positively related to the age, and that's good. We want those relationships to be as strong as possible. But we don't want age and number of bitters to be as related. That creates issues when you have two variables that are too collinear or too correlated. You can see these in this matrix scatter plot here, so you can see the relationship between age and number of bidders here or here as well. So once you have that, you want also to check the assumptions of the regression, and you can do that by using also the plot function to check the assumptions. And one thing you can do is use the plot function on the regression object that you created. And that basically creates multiple plots. You can see here hit return to see the next plot. So you hit return and basically you see the residuals versus the fitted values, the predicted. You can see that there's some nonlinearity on the data here. So that's sort of a violation of the assumptions of multiple linear regression. You can see the QQ plot. So you can see some deviations to normality. And you have other plots such as the standardized residuals versus the fitted values, and also the leverage of the residuals, which we will see and understand later.